capacitor is an electronic component that stores electrical energy. In the described scenario, the capacitor connected across the thermostat terminals acts as the snubber circuit. When the thermostat opens or turns off, it rapidly de-energizes the contactor coil. The capacitor provides a path for the residual current in the contactor coil to discharge, preventing arcing and reducing contactor chattering. Without the capacitor, the contactor may experience more frequent chattering due to arcing and electrical noise. The capacitor helps to suppress these effects, resulting in smoother operation. If the capacitor is removed or fails, the contactor may chatter excessively and potentially shorten its lifespan. To test a capacitor, a digital multimeter or an analog multimeter can be used. Let's examine the procedures for each. When using a digital multimeter, firstly, set the multimeter to the capacitance measurement function, which is often denoted as nanofarads or microfarads. Secondly, discharge the capacitor by shorting its terminals using a wire. This step is important for safety and to ensure an accurate reading. Thirdly, connect the multimeter probes to the capacitor terminals. Polarity typically doesn't matter for most capacitors, but electrolytic capacitors are polarized, so ensure correct polarity for these types. Fourthly, wait for the multimeter to display a reading. A good capacitor will display a capacitance value, for example, 10 microfarads, or a value close to its marked rating. A short-circuited capacitor will display a very low or zero capacitance value. This indicates a fault within the capacitor. An open-circuit capacitor will display an overload or infinite capacitance value, or all, indicating that the capacitor is not storing any charge. Alternatively, an analog multimeter can be utilized. Firstly, set the multimeter to the resistance measurement function or ohms. Secondly, discharge the capacitor by shorting its terminals. Thirdly, connect the multimeter probes to the capacitor terminals. Again, polarity matters for electrolytic capacitors. Observe the needle movement. A good capacitor will initially show a low resistance reading that gradually increases over time. This is because the capacitor is charging up from the multimeter's internal battery. A short-circuited capacitor will show a very low resistance reading and remain there. An open-circuit capacitor will show an infinite resistance reading and the needle will not move from its initial position. The capacitor in the described circuit is essential for reducing contactor chattering. If the contactor is experiencing frequent chattering, it is possible that the capacitor has failed. Testing the capacitor using the methods described above can help determine if it is faulty and needs to be replaced. The procedure for testing the capacitor with a digital multimeter in more detail is as follows. Firstly, ensure the multimeter is functioning correctly and that its battery is sufficiently charged. Select the capacitance mode on the multimeter, often denoted by a symbol resembling a capacitor or the letters CAP. The range selection might be automatic on some multimeters, while others may require manual range selection. If manual, select a range that is appropriate for the expected capacitance value of the capacitor being tested. For example, if the capacitor is rated at 10 microfarads, select a range that includes 10 microfarads, such as 20 microfarads. Secondly, before connecting the capacitor to the multimeter, it's critical to discharge it to remove any stored electrical charge. This is because a charged capacitor can potentially damage the multimeter or give inaccurate readings. To discharge the capacitor, use a resistor, such as a 100 ohms to 1 kilo ohms resistor connected to insulated test leads. Connect the test leads to the capacitor terminals for a few seconds. This allows the stored charge to dissipate safely through the resistor. As an alternative, some multimeters have a built-in discharge function, but using a resistor is generally safer. Thirdly, once the capacitor is discharged, connect it to the multimeter. Most digital multimeters have two input jacks for measuring capacitance. Connect the multimeter probes to the capacitor terminals. Note that for non-polarized capacitors, such as ceramic or film capacitors, the orientation of the probes doesn't matter. However, for polarized capacitors, such as electrolytic capacitors, it's essential to connect the positive lead of the multimeter to the positive terminal of the capacitor and the negative lead to the negative terminal. Incorrect polarity can damage the capacitor or the multimeter. Fourthly, after connecting the capacitor, observe the multimeter display. It should show a capacitance value in farads, microfarads, nanofarads, or picofarads depending on the multimeter settings and the capacitor's value. Allow a few seconds for the reading to stabilize. The display value should be close to the nominal capacitance value printed on the capacitor. Keep in mind that capacitors have tolerance ranges, typically indicated as a percentage, such as plus or minus 10% or plus or minus 20%. The measured value should fall within this tolerance range. Fifthly, interpret the results. If the measured capacitance is within the tolerance range specified by the manufacturer, the capacitor is likely in good condition. However, if the measured value is significantly different from the nominal value, such as outside the tolerance range, or if the multimeter displays an overload OL or zero value, it indicates that the capacitor may be faulty and needs replacement. A reading of 0 typically indicates a short circuit within the capacitor, while an OL reading suggests an open circuit. Also, look for other signs of capacitor failure, such as bulging, leakage, or physical damage. The detailed procedure for testing the capacitor with an analog multimeter is as follows. Firstly, prepare the multimeter. Ensure that the analog multimeter is in good working condition and that the battery is fresh. Select the appropriate resistance range and the multimeter. Start with a higher resistance range, such as the 1 kilo ohms or 10 kilo ohms range, and then adjust as needed to get a meaningful reading. Secondly, discharge the capacitor. Before testing, discharge the capacitor as described earlier, using a resistor or another safe method to remove any stored charge. This is important to prevent damage to the multimeter and to obtain accurate readings. Thirdly, connect the capacitor to the multimeter. Connect the multimeter probes to the capacitor terminals. For non-polarized capacitors, the orientation of the probes doesn't matter. However, for polarized capacitors, such as electrolytic capacitors, connect the positive lead of the multimeter to the positive terminal of the capacitor and the negative lead to the negative terminal. Fourthly, observe the needle movement. When you first connect the probes to the capacitor, the needle on the analog multimeter should initially deflect towards the lower resistance values, indicating a low resistance path. Then, as the capacitor charges up from the multimeter's internal battery, the needle should gradually move back towards higher resistance values, approaching infinity. This charging process is indicated by the needle's movement across the scale. Fifthly, interpret the results. If the capacitor is good, the needle will initially deflect towards a low resistance and then slowly move back towards infinity. The rate at which the needle moves depends on the capacitance value and the selected resistance range on the multimeter. A larger capacitor will take longer to charge, and the needle will move more slowly. If the capacitor is short-circuited, the needle will deflect to a very low resistance value close to 0 and stay there. This indicates a short circuit within the capacitor. If the capacitor is open-circuited, the needle will not move at all from its initial position, indicating an infinite resistance. This indicates that the capacitor is not storing any charge. Sixthly, check for leakage. After the capacitor has been connected to the multimeter for a while, observe the needle position. If the needle slowly drifts back towards lower resistance values, it indicates that the capacitor is leaking charge. A small amount of leakage is normal for some capacitors, especially electrolytic capacitors, but excessive leakage indicates a faulty capacitor. Note that analog multimeters are generally less accurate and less precise than digital multimeters for measuring capacitance. They are more useful for qualitatively assessing the condition of a capacitor, such as checking for shorts, opens, or excessive leakage. Digital multimeters provide more accurate capacitance measurements, which are useful for verifying the capacitor's value and tolerance. In summary, when dealing with contactor chattering, firstly, verify the supply voltage to the contactor coil. Under voltage can cause the contactor to chatter. Use a multimeter to measure the voltage at the contactor coil terminals while the thermostat is calling for heat. The voltage should be within the specified range for the contactor coil. Secondly, inspect the thermostat contacts. Over time, the contacts in the thermostat can become worn or corroded, leading to poor electrical connections. Clean the contacts with a contact cleaner or replace the thermostat if necessary. Thirdly, examine the wiring connections. Loose or corroded wiring connections can cause intermittent contact and chattering. Check all wiring connections to the thermostat, capacitor, and contactor and tighten or clean them as needed. Fourthly, assess the capacitor by testing with a multimeter using the procedure above to verify the capacitor is functioning properly. Fifthly, consider electrical noise and interference. Electrical noise or interference from nearby equipment can sometimes cause contactor chattering. Ensure that the control wiring is properly shielded and routed away from sources of noise. Sixthly, replace the contactor. If all other components are functioning correctly, the contactor itself may be faulty. Internal wear or damage to the contactor can cause chattering. Replace the contactor with a new one of the same specifications. Seventhly, check the control transformer. If the control circuit includes a transformer, verify that the transformer is providing the correct voltage. An undersized or failing transformer can cause voltage fluctuations that lead to chattering. Eighthly, evaluate the thermostat location. Ensure that the thermostat is located in an area that is representative of the space temperature and is not affected by drafts or direct sunlight. Incorrect thermostat placement can cause frequent cycling and chattering. Ninthly, analyze the system load. An overloaded or unbalanced electrical system can sometimes cause voltage fluctuations that lead to chattering. Ensure that the electrical system is properly sized and balanced for the load. Tenthly, consult with a qualified electrician. If you are not comfortable working with electrical systems, consult with a qualified electrician for assistance. Electrical work can be dangerous, and it's important to take proper precautions to avoid injury or damage. In the described scenario, the capacitor is a critical component for suppressing voltage transients and preventing contactor chattering. If the capacitor fails, it can lead to increased wear and tear on the contactor and potentially shorten its lifespan. Therefore, regular inspection and testing of the capacitor are important for maintaining reliable operation of the control system. In addition to the steps already discussed, consider the following advanced troubleshooting techniques for resolving contactor chattering issues. Firstly, use an oscilloscope to analyze the voltage and current waveforms in the control circuit. An oscilloscope can provide detailed information about voltage transients, noise, and other anomalies that may be causing the chattering. Connect the oscilloscope probes to the contactor coil terminals and the thermostat contacts to observe the waveforms. Look for voltage spikes, ringing, or other disturbances that may be affecting the contactor operation. Secondly, perform insulation resistance testing on the wiring and components in the control circuit. Insulation resistance testing, also known as mega testing, involves applying a high voltage to the insulation of the wiring and components and measuring the resistance. Low insulation resistance indicates that the insulation is breaking down, which can lead to leakage current and chattering. Use a megometer to perform insulation resistance testing on the wiring, thermostat, capacitor, and contactor. Thirdly, implement a snubber circuit to suppress voltage transients. A snubber circuit is a network of resistors and capacitors that is used to suppress voltage transients and reduce arcing across switch contacts. If the existing capacitor is not effectively suppressing transients, consider adding a snubber circuit to the contactor coil. The snubber circuit should be designed to match the characteristics of the contactor coil and the load being switched. Fourthly, use a power quality analyzer to monitor the voltage and current in the electrical system. A power quality analyzer can provide detailed information about voltage fluctuations, harmonics, and other power quality issues that may be contributing to the chattering. Connect the power quality analyzer to the main electrical panel or the branch circuit feeding the control system. Analyze the data to identify any power quality problems that need to be addressed. Fifthly, consider using a solid-state relay, or SSR, in place of the electromechanical contactor. A solid-state relay uses semiconductor devices to switch the load, rather than mechanical contacts. This eliminates the possibility of contact chattering and provides faster switching speeds and longer lifespan. However, Solid-state relays have different characteristics than electromechanical contactors, such as higher on-state resistance and lower overload capacity, so it's important to select an SSR that is appropriate for the application. Sixthly, implement a control system with built-in anti-chatter logic. Some control systems have built-in anti-chatter logic that prevents the output from rapidly cycling on and off due to noisy input signals. This logic can be implemented in software or hardware and can significantly reduce contactor chattering. Configure the control system to use anti-chatter logic for the thermostat input. Seventhly, perform a thermal analysis of the control panel and components. Overheating can cause components to fail prematurely and lead to chattering. Use a thermal imaging camera or thermocouples to measure the temperature of the components in the control panel. Ensure that the components are operating within their specified temperature limits. If necessary, add ventilation or cooling to the control panel to reduce the temperature. Eighthly, implement a regular maintenance program for the control system. Regular maintenance, such as inspection, cleaning, and testing of the components, can help prevent problems before they occur. Develop a maintenance schedule for the control system and ensure that it is followed. In addition to the above information, consider the following points regarding capacitor selection and application in AC circuits. Capacitors used in AC circuits, such as the one in the described scenario, should be specifically designed for AC voltage applications. These capacitors are typically non-polarized, meaning they do not have a specific positive or negative terminal and can be connected in either direction. Common types of AC capacitors include film capacitors, such as polypropylene or polyester capacitors, and ceramic capacitors. When selecting a capacitor for an AC circuit, it's important to consider the voltage rating, capacitance value, and frequency response. The voltage rating should be higher than the maximum voltage that the capacitor will be exposed to in the circuit, with a safety margin of at least 20%. The capacitance value should be chosen based on the desired effect in the circuit, such as suppressing voltage transients or providing power factor correction. The frequency response should be adequate for the frequencies present in the circuit. In addition to the voltage rating, capacitance value, and frequency response, it's also important to consider the capacitor's temperature rating in environmental conditions. A temperature rating should be appropriate for the operating temperature of the circuit. The capacitor should be protected from moisture, dust, and other environmental factors that can damage it. When connecting a capacitor in an AC circuit, it's important to use proper wiring techniques and to ensure that the connections are secure. Loose or corroded connections can cause the capacitor to fail prematurely. It's also important to protect the capacitor from overvoltage and overcurrent conditions. Overvoltage can damage the capacitor's dielectric, while overcurrent can cause the capacitor to overheat and explode. Use fuses or circuit breakers to protect the capacitor from overcurrent conditions. In some applications, it may be necessary to use multiple capacitors in parallel or series to achieve the desired capacitance value or voltage rating. When connecting capacitors in parallel, the total capacitance is the sum of the individual capacitances. When connecting capacitors in series, the total capacitance is less than the smallest individual capacitance. When connecting capacitors in series, it's important to use balancing resistors to ensure that the voltage is evenly distributed across the capacitors. Capacitors are widely used in AC circuits for a variety of purposes, including power factor correction, voltage regulation, harmonic filtering, and transient voltage suppression. In power factor correction applications, capacitors are used to improve the power factor of inductive loads, such as motors and transformers. In voltage regulation applications, capacitors are used to stabilize the voltage in a circuit by storing and releasing energy. In harmonic filtering applications, capacitors are used to reduce the level of harmonic distortion in the circuit. In transient voltage suppression applications, capacitors are used to protect sensitive electronic components from voltage spikes caused by lightning, switching, or other events. The application of capacitors in electronic circuits is governed by various standards and regulations, such as the National Electrical Code, or NEC, and the International Electrotechnical Commission, or IC, standards. These standards provide guidance on the selection, installation, and protection of capacitors in different applications. In summary, capacitors are essential components in AC circuits and play a critical role in improving the performance, reliability, and safety of electrical systems. Proper selection, installation, and maintenance of capacitors are important for ensuring that they function correctly and provide the desired benefits. The knowledge of these details contributes to a comprehensive understanding of capacitor function and troubleshooting in various electrical applications.